So hello everyone, my name is Yong-Young Noh. I'm working in Postech, South Korea. Today I'm going to talk about development of a high-performance metal halide thin film transistor. Thank you for organizing committee to invite me. So this is the outline of my talk, and after a brief introduction, I mainly talk about two different subjects. One is metal halide p-type transistor for transparent circuit, and we use copper iodide as a channel layer for p-type field effective transistor. It shows very nice hole mobility and high transparency. And secondly, we talk about 2D perovskite transistor using phenylethyl ammonium tin iodide by optimization in various film property and also the passivation of defect. We actually reported the highly reliable and 2D perovskite transistor. Then finally, and summary, and will be follow. So as you know, and oxide transistor show actually very nice electron transporting, but unfortunately, and the hole transporting in oxide transistor relatively low. So actually amorphous oxide semiconductor such as amorphous indium gallium zinc oxide successfully commercialized for OLED backplane, and it show a very high mobility over 10 square centimeter per volt per second, and especially the off current and on-off pressure really high using this wide band gap transparency oxide semiconductor. But as I said before, and the p-type transporting is not as good as n-type transporting due to some reason. So therefore, we should develop the very nice transparency n-type transistor. So this slide explains main reason why n-type transporting such a good in oxide transistor, but p-type is bad. As you can see, the conduction band minimum mainly composed by metal ns orbital, and their overlap orbital is relatively large, and also the shape is spherical. So that's the reason electron can transfer through this metal ns orbital effectively, but unfortunately valence band maximum is composed by relatively small oxide 2p orbital. But oxide 2p orbital size is very small, so it's difficult to get good overlapping between the oxide 2p orbital. That's the reason hole mobility at the room temperature is pretty much lower compared to electron mobility in oxide semiconductor. There are a few actually the p-type oxide semiconductor reported, such as copper oxide and tin oxide, and those material copper and tin's metal s or d orbital actually almost the same energy level with oxide 2p orbital. That's the reason they show quite good hole transporting, but unfortunately their mobility is not as good as our anti-metal oxide. Also, and reliable hole transporting is difficult to observe such a molecule. So we actually shift our approach a little bit using different molecule and copper iodide, metal halide. So instead of oxide to halide, we can get a better hole transporting, and through the iodine 5p orbital and the hybridization with the copper 3d orbital. So their valence band maximum is actually composed by copper 3d orbital and also and iodine 5p orbital together. So therefore, we can get a relatively good overlapping of this and the copper 3d and iodine 5p orbital, and for the valence band maximum. That's the reason we can expect a high hole transporting using this copper iodide molecule for the transparent p-type actually semiconductor. Also, the copper iodide show very nice actually hole transporting even in amorphous space, because their copper 3d orbital is actually very broad and also the complicated shape. So therefore, if film is amorphous, but orbital overlapping between the anion and cations is relatively large. So copper iodide actually reported several papers, but first paper is copper iodide actually used as a transparent conductor. They show pretty good and transparency and conductivity, and when the film is made by thermal evaporation and sputtering in solution process. And the other application is thermoelectric device is reported. Also, the spin-coated copper iodide show very nice GT value in thermoelectric devices. But as you can see, the copper iodide normal film show very high conductivity and due to the large current density. So the copper vacancy is automatically generated when you film, and then actually main source for the such a high hole concentration. So therefore, to applying this copper iodide as a transistor channel semiconductor, we should reducing hole density, hole concentration in the copper iodide film effectively. So we are making film copper iodide by spin coating method. Copper iodide mainly in the dissolving in acetonitrile solution. Then therefore we spin coating it and annealing, just evaporation of acetonitrile solvent. Finally, we can get the copper iodide film relatively low temperature, and thickness of film is controlled by concentration of copper iodide and spin coating speed. And typical film show a very low temperature processing and also the high transparency in visible region over 90%. And so it is really transparent p-type semiconductor, and their band gap is larger than 3 electron volt. And the typical film shows polycrystalline structure after the controlling the annealing temperature of copper iodide film, and the film surface is quite smooth. So then we first measure the transistor characteristic using this copper iodide as a channel of transistor with silicon oxide gate dielectric, but unfortunately it shows just conducting behavior, and there are no actually on-off actually current modulation and such a thick copper iodide films. To reducing hole density, hole concentration, we should actually reducing thickness of semiconducting films by controlling of and concentration from 25 milligram per milliliter, 10 milligram per milliliter, and also the further reducing 753 milligram per milliliter, we can get a small on-off modulation and by controlling thickness of copper iodide film. So the optimized device copper iodide transistor mobility 0.4 square centimeter per volt second, and also the on-off ratio almost 10. The performance of copper iodide p-type transistor not as good as a n-type transistor, as you can see here, but this is a kind of a first report for applying copper iodide for the transparent p-type transistor. Then we improve the on-off ratio and mobility a little bit further for copper iodide transistor by applying high K dielectric. By applying zirconium oxide solution process of gate dielectric, copper iodide transistor mobility increased to a square centimeter per volt per second, and on-off ratio also slightly increased about 100. So we successfully demonstrated and high mobility copper iodide transparent transistor by simple solution process in this work. But as I explained before, thickness reduction is one way to control the current density, but unfortunately, if we decrease the thickness further, and on current of transistor also decreased a lot. So we should find another way to actually suppressing hole density in our p-type transistor. So we use a doping method to actually reducing hole actually density. To selecting and dopant molecule, we should considering this 3 selection rule. Firstly, size of dopant must be same as a copper cation. So is this size 77 picometer size is actually suitable and for the dopant. And secondly, their valence state larger than 2 for the reducing hole density. And finally, the dopant crystal structure should be same as actually copper iodide. So typically copper iodide show tetrahedral structure. So based on this actually consideration, we think zinc gallium is actually possible dopant and for the copper iodide. Also the bismuth actually lead, even they have a different size and different crystal structure, it might be work as a dopant because their valence state larger than 2. So we try to actually use this dopant and to decrease the hole density in copper iodide film. So this is TFT calculation result for the band structure and density of state of copper iodide film. So pristine copper iodide film show the very good p-type semiconducting property and Fermi level located slightly below than a center of band gap, so it show p-type rich phase. But if you 3% copper vacancy is generated, then Fermi level is actually below the valence band maximum, so it shows p-type conducting behavior. So we can understand actually copper vacancy as actually main source for the hole and supplier. And then actually, but if we adding zinc or some dopant, the Fermi level is returned to the original position, so we can get a very nice n-type, p-type transporting semiconductor. And then actually the copper zinc is actually successfully passivating and the copper vacancy, and then actually work as a whole supplier. So by calculation, we also check the lattice structure, and this is lattice structure of copper iodide. By adding zinc into the copper iodide, the size of zinc is almost the same as the copper, so therefore lattice structure still actually remain. And but if we're adding and the lead or the bismuth slightly larger size than the copper, instead of copper in filling in the copper vacancy, and they actually show some disrupted crystal structure. So we expected a very good crystallinity in zinc doped copper iodide when the molecule, when the zinc is incorporating and proper amount. So we measure the X-ray diffraction pattern and also the absorption spectroscope and transparency and also the film morphology by adding of zinc dopant into the copper iodide film. We firstly tried to dope various dopant from zinc, gallium, lead, bismuth, and the zinc doping copper iodide show highest crystallinity in XRD pattern, and also the less than 10% doping and the crystallinity still and the same as a copper iodide film. But if your doping concentration increasing over 10 and 50 mole%, there's another peak from the zinc to copper iodide phases was generated. Then actually also it show very nice transparency, even the doping concentration up to 10 mole%, and also the transparency in the visible region. And also the morphology of film does not change too much. It shows very smooth film surface when doping concentration less than 10%. So we measure the transfer and output characteristic of transistor with various doped copper iodide film. As you can see in this transfer curve, and the zinc doped and 10 mole% zinc doped copper iodide film, very successful, and the transistor operation and the large on-operation. And so zinc and the lead and bismuth show effective current modulation, as you can see, but nickel and the gallium is actually no current modulation observed. Then, and also by controlling the doping concentration, and we can control the on-operation and the amount of on current, and 5 and 10 mole% doping effectively working transistor with a very high on-operation and a reasonably high on-drain current. And best device show mobility 5.2 square centimeter per volt per second, and on-off ratio is larger than 10 to 7, and the excellent reproducibility is actually observed. So we also reducing such hysteresis by applying ALD deposited and high K dielectric, hafnium oxide dielectric is operating very low voltage, and also the hysteresis is completely gone. So we successfully demonstrated a very wonderful p-type copper iodide transparent transistor by zinc doping. So the transistor also show very good uniformity and reliability, reproducibility. So we measured a lot of actually transistor, more than 100, it operating successfully. Then also the crystallinity of bare film and doped film is actually show very high crystallinity. So it means actually zinc incorporated into copper iodide film and effectively. So finally, we demonstrated a large area transistor array in 4-inch wafer and also the CMOS transparent inverter with indium gallium zinc oxide transistor. So as you can see, the all transistor measured in this one wafer show very good uniformity and the mobility between 5 to 5.5 and on-off ratio is almost close to 10 to 7. And also it works successfully actually well and with N-type IGGO transistor in the one substrated and show inverter gain is over 60 was observed and it show very low power consumption. We successfully demonstrated P-type actually copper iodide transistor. It is transparent and also the comparable mobility with N-type indium gallium zinc oxide.
Then let's move to the second topic is perovskite material for the transistor channel. As you can see, there are various structure of perovskite is reported, and basically the 3D perovskite is like a corner sharing octahedral structure with a cubic structure, ABX3. Then also another actually counterpart, another opposite side is a 2D perovskite. If you A cation size increased, the 3D structure is destroyed, and then layer by layer 2D perovskite is generated. So one layer is a lithium iodide or tin iodide and the corner sharing perovskite. The other layer is organic cation such as phenylethyl ammonium. So therefore this 2D perovskite has shown a better air stability compared with this 3D because this and the organic molecule can encapsulate and the inorganic and octahedral structure by moisture attack or the air attack. And another actually structure is a mixed 2D and 3D perovskite. Today I'm going to talk about this 2D perovskite transistor first, then go to the 3D perovskite. And you maybe already know, and the perovskite recently is a very hot and the emerging material for the light emitting device, also the solar cell, and mostly they use a Halide perovskite. So how to actually optimizing our tin-based and the 2D perovskite, because due to the toxicity of lead, we actually use tin instead of lead, but tin is easily oxidized from tin to tin 4. Therefore, how we reducing oxidation of tin 2 plus to tin 4 plus, and also how to passivating unwanted grain boundary, improving crystallinity of film, and increasing stability of device. We actually use systematically to adding one old method to get a very high reliable transistor. This work actually get UDC Innovation Award last year. Then, and firstly, we actually adding some self-passivation molecule inside this perovskite film and to grain boundary passivation. We adding excess and A cation, then A cation located in the grain boundary passivated electrically grain boundary very well. And secondly, we adding tin powder as an antioxidant, and also we adding Lewis base and the additive to get high crystallinity, and finally transistor and inverters and demonstrated. As you can see, 2D perovskite show perfect layer by layer structure in TEM image. Then we adding in the excess phenylethyl ammonium iodide A cation. If the A cation and molar ratio is increased from the stoichiometric, then it show the large actually the drain current. Then also the conducting AFM image clearly shows by adding this excess phenylethyl ammonium iodide A cation, the conductivity in grain boundary is increased. So we know that this actually excess A cation work as a grain boundary passivation to connecting between the grain very well. and also to reducing the oxidation of this tin 2 plus to tin 4 plus, we adding tin by using this comproplyation reaction. So if adding tin powder into the tin 4 plus oxidized tin 4 plus, it's changing to tin 2 plus. So therefore, by adding this tin powder and the solution remain and still in yellow color, it's not oxidized, but after the without actually tin powder, it easily oxidized, and even in sealed and vial. And the halide effect also, iodine and halide show best mobility compared with bromide and chloride. Then by controlling the crystallinity of perovskite film, we adding EMS or Lewis-based additive into the EMF solvent. And if we using EMF solvent after spin coating of this perovskite film, right after the spin coating, it show the perovskite paste. So therefore, we difficult to increasing grain size just using this EMF solvent. But by adding over DMS, so it's a Lewis-based. Lewis-based actually decrease the speed of crystallization of these two perovskite precursor. So therefore, after spin coating of perovskite film, still they have some intermediate state. Then after the annealing 100 degrees of Celsius, we can get the final perovskite film and the crystal phase. So by this controlling the speed of crystallization and by adding Lewis-based additive, we can get the better mobility and the better grain size. Better mobility and the better grain size. As you can see, just the DMF film, that there is a grain, small grain, and also there's some phenol. But by adding over DMS, though, it shows perfect actually the film uniformity and also the very large actually grain size. Then and the mobility, best mobility with adding this DMS, though, almost between 3 and 4. Therefore, we can improve the mobility a lot from the pair devices. And we also realizing a large area transistor and their average mobility between 3 to 4 centimeter per volt per second. And then actually the P-type perovskite and N-type IGGO make inverter together, and it show operating successfully. We still have a minute.
So this last two slides actually our best recent data. So we successfully actually make 3D tin-based perovskite transistor. Unfortunately, we cannot actually disclose detail actually composition of this material because paper is under review now. So we get mobility 55 and a very large onopolation 10 to 8, and also the other characteristic is really wonderful. And also the transistor show very nice uniformity, even measure the 100 transistor, its mobility level is almost similar. So the final, this 3D tin-based perovskite transistor show very nice actually switching behavior, and then also the under the strong bias stress condition, and the threshold voltage shift relatively very small. And one interesting thing is actually the bias transistor and return to the original and after the biases very quickly, and we don't understand fully and why this happened, but mainly we guess this is related to the defect tolerance our tin-based 3D perovskite transistor. So in conclusion, we actually introduced a systematical way to realizing reliable and 2D and the perovskite transistor in this work. This work has been done by my two brilliant students, Hui Zhu. She mainly do the perovskite work, and Ao Liu, and he mainly do the copper iodide and also 3D perovskite transistor. And thank you for your attention.